Good morning. Okay guys, today I want to take you through the RLC series circuit, or in full is called R stand for resistance, I inductance, C capacitance in a series circuit. Last lesson we looked at resistance in as a single. We also look at inductance and capacitance, but now we want to combine all of them, resistance, inductance and capacitance, in a series circuit on an alternating current. So as we start our class officially, I know you have something or some knowledge about resistance when it is alone and AC, inductance and capacitance. So as we start, we are going to find the instantaneous source voltage of the circuit, which is given by dV, or change in V, and dV is equals to dV max sine omega t. dV max sine omega d is just to show us the total voltage across the circuit, and also the instantaneous current, or the current that is passing through the circuit, is given by I max sine omega t minus the angle between the current and the voltage, with this sigma. Sigma is just to show the angle between the current and the voltage. You know, the current and the voltage are at different angles. Now we're also going to see the voltage across the resistant. In this the instantaneous voltage across the circuit passed through the resistance is given by I max R sine omega t, where I max is current maximum, R is for the resistance, and sine omega t, which shows us it is at a maximum potential. Then that is also equal to our dV max R sine omega t. dV max R sine omega d is just showing us that the current is passing across the resistance. Therefore our I max R is equals to dV R. Then the voltage across our capacitance, our inductance, is I max XL. XL show us the capacity, the reactance capacitance, or XL sine omega t plus pi over 2. Pi over 2 showing us the angle difference between the inductance and the current. Also, we're going to see the voltage across the capacitor, which is I max XC sine omega t. Now it is minus, it is not plus, it is minus. You have to see the difference between the inductance and capacitance. In inductance, we have our angle difference, it is an addition, but in our capacitance, the angle difference, it is a minus. Our angle difference, remember, it is psi, but now psi here, we take psi as pi over 2, or I have pi. Then therefore it will be equal to negative dV c cos omega t. Then on applying Kirchhoff's loop rule to the circuit, remember Kirchhoff's loop rule say that the total components across a circuit, when the addition of the circuit, or the component across the circuit, must be equal to 0. So, or must be equal to the source of that voltage across the components. For example, if we take the voltage across the alternating current here, or a voltage from AC circuit, must be equal to the voltage at R, or resistance, plus voltage at L, capacitance, plus voltage at C, which is our capacitor. Voltage across those components must be equal to the voltage at our AC source. From Kirchhoff's, remember our voltage at inductance, it was given by inductance and multiplied by change in current, which we get here as L change in current or change in T. Then Ri, which is voltage at resistance, then Q over C, which is voltage at a capacitance, which must be given as our total voltage, which is dV max sine omega t. Simple. Then we'll differentiate. Remember, at our inductance we have di over dt, so we have to differentiate for I. We get the value of I, and you know that di over dt is equals to omega I max cos omega t minus the angle difference. Then from I, our I is equals to a differential of partial differential of d over dt. You must get me right over there. Then which is the same as dq is equals to I dt, or q is equals to integral of I dt which is equals to integral of I max sine omega t minus phi dt. Now this is just an integration or differentiation of I. When we differentiate it, we will get that I max or omega cos omega t minus angle different. Then using our trigonometry, we'll get all those components and we'll get our answer to be r, the square root of r square plus xl minus xz square, and this is equal to the impedance. Now we have found an impedance, but find how to find the angle difference between the current and the source. We use the tan theta is equals to 1 over r xl minus xz. Now that is it. We have an example. You can pause the video, go through the example. Now if you have now gone through the example, the example is saying that an RLC circuit is connected to a series to a 500 Hz 900 RMS AC source if the resistance is 25 ohms, inductance is 300 mH, and capacitance is 12 microfarad. Determine the circuit impedance and the phase angle. Now we know that circuit impedance is equal to the square root of r square plus xl minus xz square. Our xl is equals to omega l, and our omega is 2 pi f. Now our xl is equals to 2 pi f l, where 2 pi f is our frequency and l is our inductance. Now that is our circuit impedance. Circuit impedance get through that one. Our xc is equals to 1 over omega c, which is 1 over 2 pi fc. We have now our xl and our xc. We'll now be able to find our impedance through the calculations. Now on finding our phase angle, now we know that tan theta is equals to xl minus xz over r. Through the calculation, we get the answer. Today I have an homework for you guys to restate that a series RLC circuit has a resistance of 425 ohms, inductance of 125 Hz, capacitance of 3.5 microfarads, omega or 377 per second, and dV max 150. We are going to determine the inductive reactance, capacitance reactance, impedance, maximum current, and the phase angle. This question carries everything you need to know in this subtopic. Okay, see you guys. Subscribe.